So this is all fine, having a generalized linear model, but what we need to do now is decide some basic fact, some basic statistical inference on the basis of this particular model. What is the corresponding statistics that we calculate similar to the R-squared or the overall F-test of significance for our linear model? In the case of a generalized linear model, we look at a few different statistics. There's a quantity called the deviance, which is 2 times the log likelihood of the model. If you recall, the log likelihood is proportional to the probability that you would observe the data given the particular parameters of the model. There's also a quantity called the null deviance, which is the fit of the model with no covariates at all, just a single intercept. As you add a parameter to the model, a covariate, the deviance is going to get smaller. This is exactly analogous to how the R-squared in a regular linear model shrinks when you add a covariate. It turns out that if that covariate has absolutely no relationship whatsoever to the response, or to the expected value of the response, then the change in deviance from the null deviance to the deviance including the covariate is going to follow a chi-square distribution with 1 degree of freedom. So this gives us a test with which we can judge whether the additional parameter, the covariate, is in fact giving us a significant change in the prediction of the model. For the bleaching data, the null deviance is 173 with 17 degrees of freedom. There are 18 data points. And the residual deviance is 15.8 on 16 degrees of freedom. So adding the one covariate, the SST anomaly, has reduced the deviance from 173 down to just under 16 for a change in deviance of 158. And if we look for how far out on the tail, what's the probability of getting a chi-squared value that large or larger from a chi-square distribution with 1 degree of freedom, that probability is 3.9 times 10 to the minus 36. So a vanishingly small probability of getting a number that extreme. That suggests that adding that covariate has a very strong effect on the expected value of the response. Here's what that distribution looks like. We have on the bottom axis here our chi-square distribution is bounded at 0 and then goes up to infinity. A chi-square distribution with 1 degree of freedom has a very high density close to 0, but then it starts to drop off very fast. And the critical value, as I say, is about 3.84. So this value or larger, there's a 0.05 probability that you would get a chi-squared value this big or larger. Correspondingly, 95% of the probability for this distribution is less than 3.84. So our value of 158 is way off to the right-hand side. How are we going to assess the fit? So we're still interested in the residuals. For Poisson distributed model or a binomial model where the number of trials on each observation is bigger than 1, we can look at the deviance residuals, which are going to be normally distributed, just as they were before, just as the regular residuals are for a normal error model. The residual deviance, that's that number that's left over, should have again it's 2 times the log likelihood, should be chi-square distributed with n minus p degrees of freedom. So n being the sample size, p being the number of parameters. So if we look at that value for our bleaching model, the residual deviance was 16. There are 18 data points and 2 parameters, so we're looking at a chi-square distribution with 16 degrees of freedom. And it turns out that a value of 16 is just about halfway, right in the middle of that sort of thing. So about 0.47 or 0.53 is the probability that we would get a chi-square value of 15.8 or larger under a chi-square distribution with 16 degrees of freedom. So that means our fit is very consistent with a binomial distribution. And that's what this looks like. So here's our probability density function. You see now it goes up much higher when we're dealing with 16 degrees of freedom. And there's our observed value there. So it's right in the middle of the probability density function of a chi-square distribution.